Any questions? Are we on? Are we live? Yeah. Any questions before we start about anything? Why do I put the chalk in that thing? Because what happens if you don't hide your chalk or take it with you, then the sort of ruthless cleaners, when they come in, they sweep it away, and it gets wasted. And these big chalks are expensive to the department, so to preserve chalk, what I do, and to avoid having to take it back to my office and remember to bring it with me, is I put it in there. Any other questions? And also, like today, for example, I didn't have to go to the little storage room and get new chalk because I knew there was plenty in here for an hour and 15 or 75-minute lecture. So I could come straight from eating lunch in College Town to class and didn't have to worry about that. So anyway. Any other questions? Okay, we are pretty much done talking about just discrete time signals and what you can do with them. So we sort of wrapped up this discussion of convolution. And today we want to go on to discrete time systems. Okay, so what are discrete time systems? And I was looking at the chapter on Discrete-time LTI systems, and I'm going to, as I look at it, I think, over the years my approach to this has evolved a little bit. So I'm pretty much going to rewrite that chapter. It won't change any of the facts. It'll just change some of the presentation, and I think it'll match a little better to what we're going to do in lecture. Okay, so essentially what a system is, and we're going to be really exact mathematically in a moment about what it is. A system is, in some sense, and those of you who took 2200 from me last spring, you heard me use these kinds of words before. It's an entity of some kind that takes input signals and produces output signals. Okay, so that's what a system is for us. And we are just, when we use the word system, we're going to be talking about the mathematical model for a real world process of this kind. So, or at least a mathematical model for such an entity. Okay, and we're going to deal only with linear time invariant systems. There's going to be a couple of homework problems where you're supposed to look at a system and say, is this linear, is this time invariant, why or why not? And that's something that's missing from the monograph right now, and that one of the reasons I want to rewrite the chapter is throw in a couple of examples of that. But so what I want to do now is I want to define carefully what a discrete time linear time invariant system is for us. So here's the formal definition. And in this context, again, F equals R or C, as always. And we could make it all complex, and it wouldn't matter, but this is the way I do it. So here's how it goes. Discrete time, linear time invariant, and I'm always going to use LTI as an abbreviation for that. It should be familiar to everybody. System, and I'm going to put in parentheses over F. So it's a system where that processes F-valued inputs into F-valued outputs, where F is R or C. Consists of the following pieces. Okay, piece number one is going to be a set X that's a subset of the set of all F-value discrete time signals. And that's going to serve as the set of possible inputs for the system. So x is equal to the set of possible input signals for the system. And x is going to have a couple of properties. We want to talk about things being linear, so there has to be a way of linearly combining inputs and getting other inputs. And what that means is x is a subspace of f to the z. And that's so we can linearly combine inputs, signals. Furthermore, to have things be time invariant, we have to be able to shift inputs and get other admissible inputs. So another property that x has to have is that it's closed under shifting. And what that means is that if x is in x and k0 is an integer time, then shift k0 of x is also in x. So x has to be a subspace, linear combos allowed, has to be closed under shifting. And finally, we want it to be big enough to contain a reasonable number of inputs of interest. So x is always going to contain all finite duration signals in f to the z. All right, so those are the properties that the input function space of one of our LTI discrete time systems has. And the other big piece is a mapping. And this is the mapping that takes input signal on the one hand to output signal on the other hand. So the mapping is going to take whole input signals to whole output signals. So it's going to be a mapping whose domain is capital X, the set of admissible inputs, and its codomain is going to be the set of all possible discrete time signals. And we call this sometimes the quote-unquote system mapping. And the idea is that when x in capital X is the input signal to the system, S of x is the output signal. These are whole signals, not just values. And this S can't be just any old mapping, right? Because we want the system to be linear and time invariant. So S has to have the following properties. So S has these properties, just as X has a couple of properties. It's linear. So S is linear. What does that mean? Whenever you take two admissible input signals, so for every choice, got to learn how to spell here, x1 and x2 in cap X, and C1 and C2 in F, we have that if you take that linear combo of input signals and apply the system to it, so that's C1 x1 plus C2 x2 operated on by S, you get the same linear combo of what happens when you apply the system individually to x1 and x2. That's linearity. And time invariance is so really it's shift invariance. So S is shift invariant. And some people, by the way, some people call them LTI systems. Some people call them LSI systems, like linear shift invariant systems. Depends on the. It's a lot more popular to call it LTI systems. It's kind of like some people say ISIS and some people say ISIL. You know, no, it's the same thing. It's the same kind of thing. Most people say ISIS. A few people say ISIL. You know, whatever. I think LSI is a little bit older terminology. All right, in the sense that for every x in capital X and k0 in the integers, if I take S and I apply it to shift k0 of x, I get shift k0 of S of x. And I'm hoping you can see and kind of appreciate how when you use this whole signal notation, you know, where you're not putting of n or of tk or whatever after everything, it makes these definitions so much cleaner. Because you can depict a whole signal on one side of an equation, a whole signal on the other, instead of saying for every n, you know, if I put x of n minus k0, wait a minute, where does the k0 come in? That always gets very confusing. So this is why I like to use this kind of notation. Okay, so that's the linear aspect of it. That's the time invariant aspect. And just reality check, it's okay to put shift k0 of x as an argument for S. Why? Because we assumed x is closed under time shifting, right? David, yes?
Can you give an example of something that's not shift invariant? Because like it makes sense to know that if you shifted, it's still like the same.
Sure. I can. Do you want me to now? He wants an example of a non-time invariant system, or non-shift invariant system. How about let's do it over here in plain view of your side of the room. How about the system that does this, that takes S of x at any time n, so S of x has specification S of x at any time n is equal to n x of n plus n minus 1 x of n minus 1. That turns out to be not shift invariant. And an easy way to show that's not shift invariant is to put a delta function in there. Okay? If I put a delta function in there, a unit impulse, I get the 0 signal as the output. Because it's the only place where the delta function is non-zero is at n equals 0. So I have 0 times 1 plus minus 1 times 0 if I put a delta. However, if I put a shifted delta in, maybe the delta is not a good example for this system.
It is that, like, if you shift the signal and put it in, you'll get something like they won't even be similar.
Well, yeah, it might not even be similar, you know.
So shift invariant means that if you were to shift the signal then put it in, it would be the same output to shift.
Yes, exactly. Yeah, that's. Let's think of it. I'm sort of anal about this. I want to make sure I make this example work for you. Okay, so I'm going to leave out the first term. Okay? Now, if I put in a delta, I get the 0 signal. It's pretty clear. Because if n is equal to 1, that's when the delta is 1, but that gives me 0. But if I put in S of shift 1 of delta, what happens? Again, I get 0. I have to make this work. I'll make it work later. If we had a 75-minute class today, I would do it now, but I'm not gonna. Yeah, I just wanted to make an easy example for you to see non-time invariance. I mean, the homework you're going to get this week, you're going to have to do this exact thing. So, anyway, okay. So that's a definition of an LTI system. some example systems, and these will be familiar to people who took 2200 from me last spring, and they're also in the monograph. So some example systems that we'll encounter repeatedly are the following. The first two are kind of trivial systems. Does anyone from last spring want to tell me what the first two systems are? One of them is zero. What's the other one? What do we call it? What do we call it? The zero system and the identity system, right? Don't you remember that? No.
Maybe it's been too long.
So it's been too long. What's going to happen when you're in year 5 of your job, and someone says, "You remember convolution, right?"
Maybe I wouldn't remember.
Yeah. Okay, so the zero system. Okay, what do we have to do to specify an LTI system? I have to tell you what the admissible input function space is, what the set of inputs is. And this one is going to be all discrete time signals. X is equal to f to the z. That is obviously a subspace of f to the z. It's obviously closed under time shifting. And S from x into f to the z specified by S of x equals 0, and this 0 here is the zero signal. And that's true for all x's. That's a system. Is it linear? Yes. Is it time invariant? Yes. Trivial to show those things. And the identity system is the other trivial one. Again, x is f to the z. Set of all discrete time signals, S. System mapping has specification S of x equals x for all x in f to the z. So this is a system that just patiently lets the input go through. It doesn't do anything to it. Okay, the next example system that we'll encounter repeatedly is the pure K1 shift. Okay, remember that one? Ricardo, you're smiling with sort of comfort of recognition. Is this? Yeah. This is a much more comfortable room than 167 and 165 Olin, in my humble opinion. But anyway. Pure K1 shift. So K1 is some given integer and x is f to the z. So this is given, this is a parameter of the system. So x is f to the z, once again, set of all systems. And S, the system mapping, has specification S of x equals shift sub K1 of x for all x in capital X. Notice that the identity system is a special case of the pure K1 shift system. You just set K1 equal to 0. All right. Okay, so those are all pretty easy, and it's pretty easy to see that this is linear. It's also shift in time invariant. If not, I could prove it to you. Do you want me to prove to you that this time invariant, just for the heck of it? Just to practice using our notation? Say yes.
Yes.
Yeah, thank you. All right, so why is it time invariant? And remember, if you don't use this sort of whole signal notation, you have to use like the two boxes and all that kind of thing to make it work. But suppose you're given x in x and k0 in the integers. What happens when I apply s to shift k0 of x? I get a signal that has specification. S of shift k0 of x at time n. Remember, this is a whole signal, S of shift k0 of x, its value at time n. That's going to be equal to what? It's going to be equal to, what does S do to signals? It shifts them by k1. So this is shift k1 of whatever's in here, shift k0 of x, evaluated at time n. And when you shift by k0 and k1, that's the same as shifting by k0 plus k1. And that gives me x of n minus k1 minus k0. And that's true for all n. Meanwhile, what if I take S of x and shift that by k0 and evaluate that at time n? Shift k0 of S of x, well, what's S of x? S of x is just shift k1 of x. And again, I have a shift of x. That's the same as shifting by the sum of the shifts. And I have to evaluate that at time n, and I get the same thing, x of n minus k0 minus k1, but that's the same. And this is for all n. Okay, conclusion. So conclusion is that if I take S of shift k0 of x and evaluate that at time n, I get the same thing as if I take shift k0 of S of x and evaluate that signal at time n. And that's for all n. And if two signals are equal for every time n, that means they're equal as whole signals. Namely, S of shift k0 of x equals, as a whole signal, shift k0 of S of x. Okay? Now, that was a long bunch of steps to prove something that's kind of obvious, but it's kind of like using practice with the getting practice with the notation. Okay? All right. Third kind of example system that we're going to encounter repeatedly is what I like to call the causal sliding window M-fold averager. Okay. Remember that one from last spring, those of you who were in the class? M bigger than 0 is a given integer. Okay, so M is a parameter of the system, just like K1 is a parameter of the pure K1 shift system. The input function space, again, is going to be f to the z, all discrete time signals. And S, the system mapping, works as follows. For every input function x, every little x and capital X, S of x is the signal with specification S of x at time n is equal to 1 over capital M, the sum from k equals 0 to capital M minus 1 of x of n minus k. And that's true for all n in integers. Alrighty, so what does that system do? What does that system do? That system takes an input signal, and the value of the output at time n, corresponding to that input signal, is the last cap m values of the input signal averaged. So in some sense what this does is it smooths out inputs. Let me write that out as a sentence. The value of the output signal at time n is the average of the values, so the previous capital M values of the input signal. And when I say the previous M values of the input signal, I mean including the one at time n. That's the k equals 0 term. So that's the causal sliding window M-fold averager. Again, it's easy to show that's linear. It's easy to show it's time invariant, relatively speaking. All right. The last of these example systems that we're going to use repeatedly to illustrate points, to do reality checks, whatever. Does anyone remember what it is? Okay. It's called the Discrete-Time Integrator. How does this go? I'm not going to tell you what capital X is right off the bat. So for now, we won't specify capital X right away. I'll tell you what it is in a second. First, I'm going to define the system mapping, capital S, and then I'm sort of going to retro-define capital X. So the system mapping S from X into F to the Z works as follows. For any admissible input function X in capital X, S of X has specification. Remember, S of X is a whole signal, so we have to tell you what it is for every single n value. S of X at any time n is the sum from k equals, and you can write this in any number of ways. I'll write it k equals 0 to infinity of x of n minus k. And that's true for all n in the integers. So the value of the output at any time n is, and I'll write this out as a sentence like I did for the averager in a second, is the sum of all the values of the input up to and including time n. What is capital X? What is the admissible input function space here? I'm going to retrofit it to be the set of all input signals, the set of all signals X for which these sums are all well defined. So define X now as the set of all X in F to the Z for which all these sums, let's give this equation a symbol. The sums demanded by equation star all exist. Now, there's a little bit of a shortcut you could do here, actually. Suppose I know that X is a signal for which the value, when I plug in n equals 0, everything is cool here. The sum from k equals 0 to infinity of x of n minus k converges. Do I know that that's true for all other n's? That I can sum all the values previous to that n? Can anything go wrong if I know that just one of those infinite sums exists? No, actually, because if you can sum from minus infinity up to any finite time, any single finite time, then you can sum from minus infinity up to every finite time. That's a little bit of a fine point. I don't want to belabor it. Okay, what do we have to do to show this is linear and time invariant? We have to check and make sure the input function space is a subspace that's closed under shifting and contains all the finite duration signals. Does it contain all the finite duration signals? Pretty clear it does, because those sums all exist. So note capital X as required contains all the finite duration signals. And it's clearly a subspace closed under shifting. So it's also not hard to show that X is a subspace of F to the Z closed under shifting. Okay, but in any event, I want to write out the verbal description of what the system does. The value of the output signal at time n is the sum of all the previous values of the input signal including the value at time n. Alrighty, so those are 4, really 5, if you count 0 and identity as separate systems. Example systems we'll encounter time and time again that'll be useful to understand. Okay. All right, so now we want to move on and talk about impulse response and related ideas. So suppose someone comes up to you on Hope Plaza, presents you with a linear time invariant system. What they do is they say this is the input function space capital X. This is the system mapping that takes X's into other signals. How do you know that it's okay to use delta as an input to that system? Let me see if I can get someone else to. Why is it always okay, given our definition of LTI discrete time system, why is delta always going to be allowed as an input? Yes? Yes, it has finite duration. And that's what you're going to say, I'm sure. Okay. Delta is always in cap X when you're talking about a linear time invariant system that goes by our definition. So given a linear time invariant system with input function space X, let's just call it input space cap X, and system mapping S, from X into F to the Z, note that delta is in X. We know that right off the bat because X contains all finite duration signals, and delta is paradigmatic exemplar of finite duration hood. David. Yeah, it will. It will change. You can think of circuits, for example, like there's no way that you can hook up a constant current source to a capacitor for all time, right? Because you're going to be, by time 0, you're going to be up to infinity. But you can hook it up to an inductor for all time. Okay, that's the idea. Like different systems are going to have different things allowed as their inputs function spaces. And in fact, the listing of examples we just did for the example systems, all the first 3 had all signals as their input function space. But the last one, clearly not every signal X is summable up to time n from n equals minus infinity. Right? Okay. So anyway, X contains all the finite duration signals, so delta is an admissible input. Thus, we can talk about S of delta. And we call that the impulse response. H equals S of delta. And we're always going to use notation H for impulse response, except when we're using it for Planck's constant. Okay? H equals S of delta. Now, what's the idea of the impulse response? The idea is that you walk up to the system at time 0 and you give it a little kick and you see what happens. So that's the impulse response. Now, it turns out the impulse response is hugely important in terms of describing the system. Why is that? Well, it turns out that the following statement is true. Here's a fact. Under no further assumptions on anything, for every finite duration signal x, and of course every finite duration signal is in capital X. So note little x is in capital X. So talking about S of x is okay. For every finite duration signal x, we have S of x equals, guess what? Guess what it's going to be in terms of h and x? Yeah, it's h convolved with x. So what does that mean? The upshot here is that if you know the impulse response to the system, then you know, first off, how it responds to any finite duration input. All you have to do is plug and chug with convolution. And as it happens, the systems we're going to be looking at satisfy this for every input signal x, but we'll get to that in a minute. Let's see why it's true for finite duration. So to see why is this the case? Well, first of all, recall that whenever you have any signal x, so for any signal x, finite duration or not, x is equal to h convolved with x, right? Sorry, delta convolved with x. Delta is an identity element for convolution. Now, if you write out the sums and everything for a finite duration x, write out the sum, this is what you get. You get that x of n is equal to the sum over k of x of k delta of n minus k. And this is for all n. And this is a finite sum because x has finite duration. There's only finitely many x of k values that are non-zero. If I write this out in terms of whole signals, what happens? X, the signal x, is equal to the sum over k. Again, this is a finite sum of x of k times shift sub k of delta. And again, this is a finite sum. That equation there equates whole signals. The x of k's on the right-hand side are just like numbers. They're just values that I'm using to linearly combine shifted deltas. So what happens when I put x into the system? This is a finite duration signal, so it's allowed as an input. So accordingly, S of x is equal to the sum over k, again a finite sum, x of k times S of shift sub k of delta by linearity of the system. Again, this is an equality between whole signals. Maybe I should be specific about this. This here is an identity between whole signals, as is this over here, as is the next one I'm about to write down. What is S of shift sub k of delta? So this is the sum over k, x of k times shift sub k of S of delta. Time invariance means I can permute shifting and S-ing, right? It's another way of looking at time invariance. Fair enough? Yeah? Okay. But what's S of delta? It's just h. So shift sub k of h. All right, so now I have an identity between whole signals. I'm going to review what it is, and then I'm going to write it in terms of combo. Going to come in just under the wire today. There's a few more people in the room than last Wednesday when we had career fair. Okay, so the bottom line is thus S of x equals the sum over k. Again, it's a finite sum. X of k shift sub k of h. That's an identity between whole signals. But if we write it out in terms of their values at time n, what do we get? We get S of x at time n equals the sum over k. X of k's are just playing the role of numbers here. Shift sub k of h, that's the whole signal. Its value at time n is just h of n minus k. And that's true for all n. And that, in turn, is just the same thing as h convolved with x at time n. And because S of x at time n is the same as h convolved with x at time n for every n, it's the same as saying S of x is equal to h convolved with x as whole signals. So that's a whole signal identity. All right. So that is a basic theorem about every discrete-time LTI system without any further assumptions. David?
I keep distinguishing that it's like a whole signal identity.
Because this is notation that a lot of people in the room.
Oh, it's a notation thing?
Yeah, you're not used to, like, at this level, when I was your age and had to walk uphill 6 miles both ways in the snow, blah, 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 people didn't write stuff like this on the board. S of X of N, that was kind of like, wait, that's too many ofs, right? But I think nowadays you grow up in this kind of CS world, you're learning how to code at an early age, eighth graders think about pointers to arrays of pointers to arrays of pointers, everything, right? So you're used to this kind of thing, and it doesn't bother you. But anyway. How many levels of arrays of pointers to pointers? Anyway, let's leave that for next time. Okay. Don't they teach C to 8th graders?